Hi, my name is Mertcan Temel. I am a PhD student at UT Austin. I will present our paper titled Automated and Scalable Verification of Integer Multipliers. My co-authors are Slobodova, my supervisor from Center Technology, and Warren Hunt, my PhD advisor. Algorithms such as Booth encoding and Wallace tree are used to create efficient multipliers for hardware. Even though these algorithms have a long history, verification of multipliers has been an ongoing challenge. SAS solvers and BDDs are full automatic, but they do not scale for complex multipliers. Equivalence checkers are used for some industrial designs, but with a lot of manual effort, and this approach is very design specific. Computer algebra methods have shown much better results, but they will present certain challenges and limitations. We propose a different approach. Our method is more efficient and more widely applicable. We have tested it for over 75 different benchmarks with very successful results. It scales much better than the other state-of-the-art tools, and we can verify various 1024 by 1024-bit multipliers in less than 10 minutes. We implemented and verified our method on the theorem proving system ACL2. This gives a soundness guarantee to our proofs. Our targeted multipliers are RTL-level hierarchical designs. In this presentation, I will first review the integer multipliers and common algorithms to design them. Then I will describe our method in detail. Finally, I will show our experiment results comparing the performance of our method to the other state-of-the-art tools. The goal of integer multipliers is to efficiently multiply 2-bit vectors for hardware applications. We can divide these modules into two parts: partial product generation and summation. Algorithms such as Booth encoding are used to generate partial products, and algorithms such as Wallace tree sum these partial products. On this figure here, you see an example of a Wallace tree multiplier that multiplies two 3-bit signed numbers A and B. These numbers are sign extended by repeating the most significant bits. Then partial products are created by multiplying each bit with each other like grade school multiplication. Each of these dotted lines are partial products. In hardware, these partial products cannot be summed in a single step. Therefore, Wallace tree algorithm is used for parallel additions. Groups of bits are selected from these partial products and inputted to half and full adders. The result of these bit-level additions are inputted to another set of adders. And this is repeated until we have two rows. Then we use a vector adder, also called a final stage adder, to finish the summations. These algorithms may create very complicated structures for verification systems. For example, if we swap some bits on the same column between half and full adders, then we will get a functional same, but structurally very different designs. So it is important to develop an automated system that has minimum assumptions about the structure and can work with a wide range of multipliers. We aim to verify that multiplier designs are functionally correct. We do that by proving a conjecture of this form in ACL2. ACL2 is an automated and interactive theorem proving system with over 25 years of history and wide industrial use. On the left-hand side of the equality, we see the evaluation of the design in SVL format. This is translated from system Verilog so that designs can be interpreted in ACL2. SVL run function evaluates this design for any bit vectors A and B. On the right-hand side, we see the specification represented with the built-in multiplication function with appropriate sign extension and truncations. The length of the vector A is m, and the length of vector B is n. We prove these conjectures for constant m and n values. This conjecture is submitted to ACL2 using a DefSum event, as you can see here. DefSum stands for defined theorem, and it is the common way to prove theorems in ACL2. This executes our verified tools, implementing our rewriting algorithm to simplify and prove multiplier designs correct. We have two main steps to prove such conjectures. The first step pertains to the adder modules only. Before reasoning about the multiplier modules, we deal with modules such as full adders and final stage adders that are used by the summation tree algorithms. Then we start working on this conjecture about the multiplier module as given here. Our candidate designs retain circuit hierarchy, and we take advantage of that. In our system, if a submodule is already proved to be equivalent to its specification, then we can replace its instantiations. So we rewrite the instantiations of all adder modules reasoned in step 1. Then using two sets of rules that work together, we simplify summation tree and partial product generation algorithms. After rewriting the circuit description, we rewrite the right-hand side to the same form and conclude our proofs. We developed a heuristic that we have observed to work with various multipliers, and this is what I'm going to describe here. Let's go over these steps in more detail. Our first step is proving adder modules equivalent to their specification. We do that by stating a similar conjecture for adders. Here, we choose a specification for each adder module that is represented by our functions s, c, and plus. S stands for sum bit, and it is an alias for mod2. C stands for carry, and it is equivalent to floor of divide by 2. This table gives examples of these specs for some common adders. A half adder has 2 inputs and 2 outputs, and its sum and carry bits can be represented this way. The same goes for full adders, which have 3 inputs instead. Vector adders or final stage adders also have a fixed specification for each output bit, as seen here for the first 4 bits. A multiplier might have different adder components, but coming up with these specifications are often trivial. We prove such conjectures about adders with a set of rewrite rules. This method is described in our paper, and we omit the details here in order to save time, and we focus on multiplier proofs instead. When such def-thumb events succeed, they are saved as rewrite rules. So whenever we run into a CL run of an adder module while rewriting the multiplier modules later, we can replace that instance with the specification of the adder module. After the adder modules, we can now start verifying the multiplier module itself. This is the conjecture that I have shown earlier. Our goal is to rewrite both sides of the equality into the same final form and conclude our proofs with a simple syntactic check. An example of this final form for each output bit is given on this table. The least significant output bit, out0, is the summation of the first column of partial products, which has only one bit, A0, B0. The second output bit, out1, is mod2 of the summation of the second column, A1, B0 plus A0, B1, plus the carry from the first column, and so on for the other output bits. A mathematical definition of this form is given in the paper. We prove this to be equivalent to the built-in ACL2 multiplication function. So whenever we see the multiplication of 2-bit vectors as seen on this conjecture, we replace them with this form. So now, let's go over our rewriting algorithm that can convert various multiplier designs into our final form. First, let's assume that we have a Wallace tree multiplier with simple partial products. After rewriting the adder modules with their specification from step 1, we may get this term at the top for a multiplier output bit. Our goal is to simplify this term and convert it into our final form. We observe that such terms have many nested calls of the function s. We can get rid of such nested calls with this lemma. Basically, the arguments of the inner calls of s can be extracted. After applying this lemma, we get the simplified term at the bottom. This term still doesn't look like the final form, and we see the summation of these. Since our final form does not contain such instances, our intuition tells us that we should try to remove these somehow. We introduce a new function d, which is equivalent to divide by 2. Remember that c is equivalent to floor of divide by 2. C and d can be rewritten in terms of each other, as seen in the last lemma. So whenever we see a summation of 2 or more c's, we convert them to d, and we add them together. And we do that for all other summations, c plus d and d plus d as well. Then we convert a single instance of d back to c whenever possible with the last lemma. When these lemmas are applied to the term at the top, we get the term at the bottom. This matches our targeted final form, so we can conclude that the multiplier is correct for this output bit. It may not be evident by this example, but this method works for very large multipliers as well. Rewriting with these lemmas and some additional rules about commutativity and associativity of addition, we have simplified and verified 1024 by 1024 bit multipliers, as you will see in our experiment. Even though I have shown as if these lemmas are applied one after the other, they're actually applied in an indeterminate order. Rewriting is done from inside out, and we apply any one of these lemmas when they are applicable to the term, so we don't have to traverse large terms over and over again. The lemmas shown so far are only sufficient when the multiplier uses simple partial products. Some partial product generation algorithms, such as Booth encoding, may create much more complicated terms. An example of such a term after all other simplification took place is given at the top. It is much dirtier than our final form. Our first step is to get rid of old extraneous logical operators, such as XOR, OR, and NOT, with these three lemmas. Then we obtain a term at the top that is composed of only S, C, plus, minus, and logical AND functions. Again, we try to convert such terms into our final form. The first three lemmas pertain to subtracted arguments. Whenever we encounter such an instance, we drop the sign for S, C, and D functions, and we add that instance to the term itself for C and D functions. The last three lemmas pertain to repeated arguments. For S, the duplicates simply cancel each other. For C and D, the duplicates are removed from the arguments, and a duplicated element is added to the term. After applying these lemmas, we get the term at the top. We get the term at the bottom. This matches our final form for the second output bit of a multiplier. And this concludes our methodology. All the lemmas for multiplier module proofs given in step 2 work together, and we do not require any user guidance about what algorithm is used in the design. Now let's see the performance of this method by checking our experiments. We have tested our method for over 75 different benchmarks. These include multipliers with signed or unsigned simple partial products and Booth encoding. Summation tree algorithms such as array, Wallace tree, Dadda tree, 4-to-2 compressors, and overturned state trees, and so on. And final stage others such as breadcrumb and Lander-Fisher. The complete list is given in our paper. Not only do we show the wide applicability of our approach, but we also show that our method is very fast. For that, we measure the total time to verify all the modules in a multiplier design, including proofs for each other module, and a final proof for the multiplier module. We compare our method to the other state-of-the-art tools. These two are computed algebra-based methods that appeared in DAC 2019 and FMCAT 2019 respectively. The first one only works with unsigned multipliers, and they do not produce certificates, so there is no way to check the correctness of their proofs. The second one demonstrated a great improvement over the previous studies in terms of both the performance and the ability to produce certificates. Since our method is verified, we also included the time to verify those certificates for their tool. Here we give the average timing results for each multiplication size from 64 by 64 to 1024 by 1024 bit multiplication. The other tools could not verify some of the benchmarks, either due to some program error or timeout. So we also show the success rate on separate columns for each tool. The other columns show the average timing result in seconds for the benchmarks that the tools could prove. As you can see, our tool is orders of magnitude faster than the other tools, could verify all the designs, and has a much better scaling factor. Kaufman's tool could run most of the benchmarks, but started to time out for some Booth encoded designs after 256 by 256 bit multipliers. That is why it looks like they are getting faster for 512 by 512 bit multipliers. Their averages just do not involve the slow multipliers at that point. In order to make a better one-to-one comparison with Kaufman's tool, we implemented the 8 benchmarks that they could run for all the sizes and calculated the averages for those benchmarks only. This is given at the bottom. Our tool already is faster by a factor of 6 for small designs, but it scales very well. And for 1000 by 1000 bit multipliers, we see that our tool is 40 times faster on average than the fastest tool available. We can find the results for individual benchmarks in our paper. The complete table will show that our tool is more consistent and gives more similar results for all the multiplier types, whereas the other tools give more fluctuating results for some benchmarks with different algorithms. In conclusion, we have proposed an efficient method for the verification problem of integer multipliers. We have not proved the completeness of our method, but we have shown that it can work with a wide range of multipliers that implement algorithms used in the industry. And very importantly, our tool is verified using the theorem proving system ACL2. Getting these results required overcoming many technical difficulties, and keeping the program verified while maintaining optimum performance was the biggest challenge. In the end, we are glad to have a publicly available tool that can reliably verify these complex designs. As per the future work, we would like to generate counterexamples in case of a buggy design to help guide the users find the bug, and we'd like to support completely flattened designs. Thank you all for listening.